Okay, guys, back up a little bit here. We're going to do a review of chapter 9 and 10. This will be your asynchronous assignment. And let's start. I'll pause here. Okay, guys, so I've already gone through when I did the original chapter 9. I went through most of, if not all, the questions starting on page 133 and 134. I might not have done them all, but I think I got you in the right direction in those. Tell me if I'm wrong on that, but I seem to recall doing that. So on page 138, I don't think I did these questions. Question number 1, a pair of 6 megahertz probes are identical except for the active element diameter. Sorry, I paused there. My wife is standing behind me ready to ask a question. So a pair of 6 megahertz probes. So a pair of 6 megahertz probes, we know that they have this same thickness. All right, so why? Because they're 6 megahertz. That's the fundamental frequency anyway. And the determination of frequency comes from that thickness there. I need to get rid of my little duplicator there. That thickness from here to here determines frequency. So both of these have the same thickness. So, but they have, I think we're going to read, a different diameter. The active element is 6 millimeters and 10 millimeters respectively. And the other word for diameter in this case would be aperture. The sound beam of which probe will have a shallower focus? Okay, so we don't really need any. Those numbers is 6 and 10. I'll talk to them later. The 6 and 10, all it tells us is that one diameter is bigger than the other. So let's call this one over here, we'll call that 6 millimeter diameter. And then this one is the 10 millimeter. Well, let's see, what do we know about the diameter? The diameter is directly related to the near zone length. And so here I've already drawn in on this smaller diameter, I've drawn in the near zone length, which is the green arrow down the middle, which is pretty much synonymous with the near zone. And by the way, I did not draw this very well to scale because well, anyway, shut up, Kurt. Just stick with what you're sticking with. Okay, so on this one, though, I'm going to put a little dot right here to remind me where I want to go. In fact, I'm going to get my little cheater. I'm going to cheat on this one a little bit and create a a beam profile. A little more like that. Should have used my cheater to smooth out that line, but in any case, the focal zone is farther away, therefore, of course, I'm moving this thing around instead of, what's going on? Drawing, okay. So the probe with the 6 millimeter active the 6 millimeter active focus has a shallower focus. Smaller diameter crystals produce beams with shallower focus, okay? And so that's just kind of shows just what that looks like. Let's see the next one, number 2, a pair of 9 millimeter diameter probes are identical except for frequency, which is 3 and 6 megahertz respectively. Which beam will have the shallower focus? Okay, so let's just come over to these two guys. These two have the same diameter. I know they do because they were copies of each other, and I just erased sugar. I wanted that little thingy to come with me, and I forgot I have to pull it over first. Okay. Okay, so let's see, thicker diameter. Now let's just kind of, I'm going to put this, what happened to my little guy? He's way over here. And this is where we hit pause. Okay, so same diameter, both of them are 9 millimeters. I won't have to write that in, but which one's the 3 megahertz and which one is the 6? Which one is the 3 and which one is the 6? We learned earlier that higher frequencies, that would be the 6 megahertz of the 2 that I've drawn. And this is the 3 megahertz. Higher frequency, thinner element. Just like a thin, small bell creates a higher frequency sound than a large, heavy bell makes a lower sound. Okay, so which one of these creates the longer, or what's asking? Which beam will have the shallower focus? So which one has the shallower focus? Okay, well, let's go ahead and just draw it in. There's a typical beam profile. Obviously, I'm just making this stuff up as I go along. For a thicker, but a thinner, surprisingly, has a much longer focus. So which one has the shallower? I guess it should be the 3 megahertz has a shallower focus. Goes a little bit against what common sense would tell us. Okay, number 3, which of the following probes creates a beam with the deepest focus? Ooh, okay. So deep focus. Well, all they're asking is to add, well, to what combination is going to create the deepest focus? Well, higher frequency created a deeper focus. And then what else? A wider diameter, a 10 millimeter diameter versus a 6 millimeter diameter. So a wider diameter. So whatever combination they show that has the highest frequency and widest diameter. And it looks like, oh, I almost jumped to the wrong one. So let's go with diameters first. 4, 6, 6, and 5. That's A, B, C, and D. 4, 6, 6, and 5 millimeters. Well, okay. So now this one, you won't necessarily be able to just drop down to 2 and say it's either B or C, because then we look at our frequencies and you have 4, 8, 2, and 8. So the 8 is the highest frequency. The 6 is the highest diameter. So in this one, B looks like it would create the longest focus. Okay, number 4, which of the probes creates a beam with the shallowest focus? All right, well, now we're looking for the opposite. We're looking for the lowest frequency and the smaller diameter. So the smaller diameters, 4, 6, 4, and 5. But then frequency, 4, 8, 2, and 8. So 4 is our smallest diameter, and our lowest frequency of all of them is 2. So it looks like letter C, 4 millimeters, 2 megahertz. Those combine to create the most shallow focus. Okay. Number 5, which of the following probes creates a beam with the shallowest focus? This is just the same thing. Let's see, small diameter. We're going to go with either A or C. I'm sorry, shallowest focus. Yeah, shallowest focus. We're going to go with A or C. Small diameter creates a longer, shorter focus. And then what else creates a shorter focus? A lower frequency. So letter C says small diameter, low frequency, and C is the correct answer there. True or false, active element diameter and near zone length are directly related. Okay, well, yes, so the answer is yes, but look, when we say directly related, that means larger diameter, larger focus. So those are directly related. Number 7, transducer frequency and near zone length are inversely related. Okay, so inversely related. So I got to be careful how we read that, right? So frequency, high frequency, high or long near zone length. So the higher the frequency, the longer. I'll put my arrow this way. I see that doesn't make sense. I don't like that. Well, you get it. Higher frequency, higher near zone length, or longer near zone length. So they're actually directly related, aren't they? And then wave length and near zone length are inversely related. Ooh, okay. Now let's slow down. I want to get rid of some of my little green drawings in there. Wavelength and near zone length are inversely related. So, wavelength, lambda in a 6 megahertz is less than, right? And near zone length in this case was longer. So we have a smaller wavelength creating a longer near zone length. So smaller and longer are inversely related. So yes, they are inversely related. Okay, let me put on pause and see what the next set of questions we're going to do. Okay, page 141. First question, I'm going to try to draw 2 pictures on one space and hopefully it doesn't make too much of a mess. A pair of 6 megahertz probes. So, okay, the probe is going to look the same in regards to its thickness, but not its width. So we'll see if I can do this. A pair of 6 millimeters are identical except for the active element diameters, which are 6 millimeters and 10 millimeters. Well, I'll tell you what, all I have to do is add a little bit of extra element out here. Okay, yeah, that doesn't look great. Let's do this just to kind of clean this up. Shoot, I was on that stupid helper. Doesn't always help. Okay. Looks like I'm drawing the front end of a car here. So let's do which beam will be more compact in the far field? Oh, okay. All right. So what they're asking here is how far will the sound beam flare out? So let's use this section as our first transducer. And so let's see if I just want to make sure we are saying everything correctly. So on a smaller diameter, let's see, we have let's just put my focal point right up there. Okay, not exactly to scale here, guys, but thank you, darling. Just get myself a little much. All right, not exactly to scale, but that's okay. We're gonna exaggerate this a bit. So if that's my beam diameter in for a more narrow width or aperture. And then a beam diameter here for this guy. Let's see, I'm going to put it on focus down here. Okay, so let's see if I've drawn that halfway decent. What this question is asking is how quickly the beam diverges. I think I told you this before, but in case you didn't catch it, for whatever reason, frequency or aperture, or even in actively focused transducers, the closer the focus is to the element, once you pass that focus, let's see, let's use green here, the beam spreads at a faster rate of speed. When the focus is further away, whether it's diameter doing it or frequency doing it, does not matter. It still spreads out, but at a slower rate of speed. This goes back to, remember, there's a question, not so much as a question, but a statement in the book. I want to make sure you guys understand this. Today we talked about the idea of lateral resolution, okay? And higher frequency transducers have a longer focal point, therefore a less of a divergence in the beam, and therefore higher frequencies do have better lateral resolution, but it's really only noticeable in the far field. Okay, I'm gonna put pause on, now I'm gonna take a bite out of my lunch. Okay. Question number 2 is the same question. Well, it's not, I basically already answered it. Whether it's frequency bringing us up here or down here, or beam diameter. Same thing. The closer the focal point is to the transducer, the faster the divergence. So I don't need to write anything down for 3, 4, and 5. I think which of the following probes creates a beam with the least divergence? Okay. In other words, which one produces the longest focal zone? Longer focal zones, least divergent. We already discussed this really. So let's see. Longer focal zone, that's a higher frequency and a wider diameter. These two produced long focal zones. So you add those together. Let's see. I'm just going to jump straight. Oh, which one are we on? We're on number 3. B, 6 millimeter diameter, and that's the largest diameter they give. The 4, 6, 6, and 5. And then we're going to want the highest frequency, 4, 8, 2, and 8. B, 6 millimeters, 8 megahertz. So you can see where it's the same exact question as we've already answered. So let's jump down. This 4 and 5 are the same. Let's jump down to 6. Transducer frequency and beam divergence are inversely related. Transducer frequency and beam divergence. Yes, so what they're asking here is a higher frequency. If it were a higher frequency, creating a higher or longer near zone length, then they would be directly related. Oh, but I'm sorry, yes, see, I just got myself wrapped up in here. Higher frequency actually produces less divergence. Lower frequencies produce more divergence. So in that way, they are inversely. So higher frequency and divergence of the beam is inverse. Number 7, active element diameter and beam divergence are inversely related. Same type of question there. I want to jump to, let's see, page 143. Review. Here, let me pause and see which questions I want to do. So page 143, these are kind of funny questions. Each one starts 1 through 4. The frequency of a transducer does not change. He wants to make sure that we're not confusing issues here. If the diameter of the new piezoelectric crystal increases, what happens to the near zone length? Well, it increases. We've discussed that. That is right here. The frequency of a transducer does not change. If the diameter of the new piezoelectric crystal increases, what happens to the beam diameter in the far field? It decreases. Okay, so they're saying it decreases. What they're really saying is, well, they're saying here. In other words, it doesn't, it's not so much that it decreases. I don't like that term, but it doesn't increase as quickly as a more narrow transducer would. The frequency of a transducer does not change. If the diameter of the new piezoelectric crystal increases, what happens to the wavelength? Really shouldn't have anything to do with it because it's diameter, not thickness. Diameter does not change the wavelength. Thickness does. Frequency of a transducer does not change. If the diameter of a new piezoelectric crystal increases, what happens to the beam diameter in the near zone? Well, so in the near zone, this diameter corresponds to this larger aperture. It's going to be, so if this larger aperture increases, then the diameter in the near zone, of course, is going to increase as well. Next page, 144. At one location in the sound beam, is the sound beam diameter 3 times greater than the transducer diameter? Ooh, that would be, let's see, at the end of the near zone? Nope. At the end of the near zone is the focus. It's actually half, right? At the depth equal to 4 focal lengths. Ooh, focal length, that's another term. And this one, I've been calling that the near zone length. It's also called a focal length. Keep that in mind. What was I saying? Let's see, at the 4 focal, well, why would it be 4? At the end of the far zone? No, at the end of the far zone, does the far zone have an end? That's never really defined, but yeah, at the end of the far zone, that's not really an answer. If you say the end of the far zone is 2 near zone lengths, then no, that's back to the original aperture size. And at triple diameter depth, what the hell does that even mean? 3 times greater than, I don't think triple diameter depth, we've never heard that term before. Well, let's see, the answer is B. The only reason where the beam diameter exceeds the transducer is at depths exceeding 2 focal lengths. Okay, so B seems to be a little bit made up. However, it's the only possible answer. Although you know, if I were taking this test and I saw D, I'd have to, it would give me pause. I'd have to think, well, triple diameter, that sounds, triple dog dare you. Anyway, number 6, what is the shape of the sound being created by a tiny piece of piezoelectric PZT, I'm getting my PZT. Well, let's see. I know that he said it was V-shaped. I could just go that by memory on that. Yeah, but what he's really saying there is a tiny piece does not act, a single tiny piece of piezoelectric material does not act like a large piece, okay? So this is a little bit different because a large piece acts with Huygens wavelets. It acts as if it is hundreds, thousands, millions of point sources. Small pieces don't do that. Small pieces have a beam that spreads out. He's calling this basically an upside down V. Why doesn't he just call it a pyramid? I don't know. But that's the difference. A small individual piezoelectric element will spread out just like the sound that pretty much all sounds that we're accustomed to hearing spread out. Which of the following explains why a sound being created by a disc-shaped crystal is hourglass-shaped? Well, it's just Huygens. Which of the following locations is deepest? End of the Fraunhofer zone. End of the Fraunhofer zone. I have to go back and reread something. That's not how I read it before. Okay, which of the following, but that makes sense. Near zone is Fresnel. Far zone is Fraunhofer. And so at the end of the Fraunhofer, which should be the deepest eye, following locations is most shallow, beginning of the, let's see, beginning of the far zone, probably not. Beginning of the focal zone, okay, well that could be. The focal depth, no. Beginning of the Fraunhofer zone, which is the same as the far zone, so it's gotta be B. So what they're saying in this question, just zoom in a little closer on this guy. Of the 4, actually 3 of them are all the same. Beginning of the far zone is right there. The focal depth is right there. Beginning of the Fraunhofer zone is right there. It's 3 different ways of saying the same thing. However, letter B is beginning of the focal zone, which is right here. So that is the shallowest. That is 9. I said I was going to do 10 as well, right? Let's pause. And before we begin 10, I just quickly looked up his definition in 2 locations. His definition of the far zone or Fraunhofer zone. he's very careful not to say the end where the end of the Fraunhofer or far zone is. He just says it and it goes on. So in these questions, it's really suggesting that the far zone goes from the focus to 2 near zone lengths. Okay, well that's probably it. I wish he would have said that a little more clearly. I'm going to look up the definition somewhere else too and see what other authors have to say and whether or not it's just that specific depth or if it's from the focus all the way through to forever. Actually, let me check on that right now. Hold on. Okay, I only spent a couple of minutes looking that up. And other authors don't really address it either. I think maybe no one knows. Only Fraunhofer knows, and he's dead. So yeah, Fraunhofer is the far zone, and whether or not it ends at 2 near zone lengths or it continues on forever, I still don't know. Okay, chapter 10, page 149. Let's see, what is the ability to accurately distinguish two structures lying close together called? That's just in all resolution, also called spatial resolution. Spatial. The reason we have to say spatial resolution is that, wait a minute, there I am. The reason we have to say spatial resolution is because there are other resolutions. There's temporal resolution, which is kind of your frame rate. Really bad temporal resolution, it's hard to look at. But I digress. I'm going way ahead. We're talking about spatial resolution, the ability to see something from here to here. Well, that would be like lateral resolution, or something from here to here. That'd be more axial resolution. So let's see, the ability, number 2, the ability to distinguish two structures lying close together front to back, or parallel front to back. What the hell does that mean? But parallel to the sound beam. In other words, with the sound beam. Was it LATA? Longitudinal axial, or no, it's LARD, I'm sorry, LARD. Hey, LARDO, longitudinal axial range, radial, or depth resolution. That is resolution, as the beam is coming down this direction. We have something here and something here. Can that beam figure out that there's a dot and a star, or does that beam instead see the star? Did you see the star? Number 3, axial resolution is measured with units of, well, distance. Any of our spatial resolutions are going to be distance, generally in millimeters for us. There are more cycles in a pulse. If there are more cycles in a pulse, the numerical value of range resolution is range resolution. That's part of LARD, range resolution. If there are more cycles in a pulse, the numerical value of range resolution is greater. Interesting. Spatial pulse length. Yeah, so, okay. So axial resolution in millimeters equal to spatial pulse length divided by 2. So anything that is up here is going to increase there. So the numerical value of axial resolution goes up. Ha! The numerical value goes up. But I guess it's like golf. You don't want golf. I don't do sports. I'm good at sports. I just don't watch them. I never played golf. Yeah, you don't want a large number in golf. You want the small number. So a spatial pulse. Well, spatial pulse length, of course, is increased because we just said. What was that question say? Right page. If there are more cycles in a pulse, if there's more cycles in a pulse, your spatial pulse length will increase. The number for your axial resolution will increase, but that's not good. You want your number to be small as possible. If your axial resolution is 10 millimeters, you ain't seeing anything with any kind of clarity in the body. But if your axial resolution is 1 millimeter or half a millimeter or even less, now you're starting to see really nice detail. Number 4, if there are more cycles in a pulse. Did I just do that one? I did. Number 5, if a new pulse transducer, pulse transducer has many more cycles in its pulse, The image accuracy degrades. So I just said that. If you have more cycles, in other words, spatial pulse length goes up, your number might go up, but that ain't good. Quality or accuracy they use. I just put 2 R's and 1 C in accuracy. As soon as I wrote it out, I knew that was wrong. Accuracy. For sake. Anyway, your accuracy goes down. Let's just go to the next one where I'm not losing my mind. High-low frequency transducers generally have the best range resolution. High. We always want the highest possible for the application. We just have to account for attenuation. Which of the following transducers has the poorest axial resolution? Ooh, interesting. Interesting. In fact, I'm going to write this one out. Let me pause it here for a second. Okay, so I've written out the basics that we need to look at for number 7 on page 149. Which of the following transducers has the poorest axial resolution? Now, they're not asking for any numbers, but I did throw some numbers down so we can look at that as well. But let's see, what are we looking for? The following has the poorest axial resolution. So we want a larger wavelength, larger wavelengths. We just inherently know from the beginning of semester that the higher wave length, in other words, the lower frequency or the lower megahertz number is going to be worse off in general. So in general, we're looking at either probably we're looking at this one or this one. The other thing we worry about is cycles. We want as few cycles as possible. The more cycles, the worse our resolution. So let's see, 4, 3, 5, and 2. Well, that's not good, but this one's even worse. So letter C is the answer. I decided to take it just a step further and say, okay, well, what does that even mean? Well, let's think about what this means here. Wavelength is the speed of sound, 1.54 millimeters per microsecond, divided by the frequency. So in the case of we're just going to say frequency here. In the case of 1.7, it actually turns out to be a wavelength of 0.9 millimeters. Right off the bat, you have poor resolution. There are spatial pulse lengths with the waves, several cycles, I should say, combined that equal less than 0.9. So right off the bat, now we have to do 4 times that. So 4 times 0.9. I guess I should just realize that it's 36 with a point. So, so the spatial pulse length, remember, because it's wavelength times cycles, and we figured out what the wavelength is. Spatial pulse length is actually equal to 3.6 millimeters. That's actually not too good. We want to be able to see better than that. But if you really need to go deep into the body, that's the way to go. And of course, 1.7 or 0.9 times 5 is going to be even worse. So let's just, for the fun of it, look at the other ones. So let's look at the best one we have up here. And still, 2.6 megahertz is not exactly not exactly fine detail type imaging, but it's the best we have here. That wavelength, when we do 1.54 divided by 2.6, so if I said 2.6, that's going to equal a wavelength of 0.6 millimeters. So better. This this number here is better than this number here. So far we have better resolution, and we have two cycles. So I guess what's that? So the spatial pulse length. I'm measuring, I'm multiplying these, right? Yes, I'm multiplying wavelength times 2, so that's 12, so it should be 0.2. I am correct. I panicked. The reason I panicked is because I looked at the wrong number above me. I'm like, wait a minute, that doesn't work out. Of course, to spatial pulse length. So the resolution here is much better than there. Still not great. 2.6 megahertz is a very low frequency. 1.7 megahertz is I don't know if I've even used a transducer that goes down that far. Okay, number 8, in soft tissue, a 3-cycle 1 megahertz pulse has a pulse length equal to 4.5 millimeters. What is the axial resolution? Right off the bat, I'm thinking I have some BS information here, or some unneeded information. Let's say that. We won't call it BS information. We know that 4.5 is the spatial pulse length. Well, what did we find out what axial resolution is? It's basically spatial pulse length divided by 2, right? So let's just pull out our calculator because I'm not doing that in my head. 4.5 divided by 2. 2.25, and I only see, yep, that's letter C. So 4.5 millimeters divided by 2 is equal to 2.25. The reason it's divided by 2, and it's a little, I think it was a little hard to imagine, but when we have our wave coming down, let's see if our spatial pulse length is that long. Well, then we have this, it kind of comes through, and it's going to have a reflection. You know what? I'll draw the reflection up there. That might seem a little better. This one's got to come down and turn around, but you can see from this picture, it seems like we are not going to catch up with each other, and so there's going to be 1, 2 echoes with this picture. If on the other hand, of course I didn't leave myself any room here, but if I have a longer, and let's put the echo is starting to come back up over here, but I also have, this guy is coming down, turned around, and he's basically caught up with this one because let's see, what I've tried to draw is the length from here to here is about equal to here, around the corner to there. And so it has caught up with its previous echo, not because of different speeds, but because, you know how some people draw it. Let me just do this one more time. Sorry about this, guys. I'm just thinking on my feet here, and some people draw it like this. I don't know if that makes more sense. as this guy is going along, and this guy's coming through, this is basically an incident beam. An incident beam was coming down this way. It hit here, it is reversed. It's reversed, it's reflected. Some of that sound went through, hit this one, it's reflected, and it catches up. You can see that this is going to catch up with this tail. As we go further along, here's that first echo, and there's that second echo. They're basically attached. They've become one long echo. Let's see. Oh God, lateral resolution, focusing. Chapter, page 157. What is the lateral resolution at depth of 8 centimeters? We gotta look at this picture here. So, what is the lateral resolution at depth of 8? If you're looking at the picture, there's a 9mm aperture. 8 centimeters is the focus. It's the 1 near zone length. So it is going to be half of the original aperture, so 4.5 millimeters. Follow along on page 157. What is the lateral resolution of 16 centimeters? That's 2 near zone lengths. It's going to go back to the original diameter. What is the best estimate for the resolution at 4 centimeters? Resolution at 4 centimeters. So they're not asking you to do any math here. You're just really you're gonna just kind of guesstimate. So it starts off at 9 millimeters. At 1 near zone length, which is 8 centimeters, the lateral resolution is 4.5. At 4 centimeters, it's got to be between those. Less than 9, greater than 4.5. And the only answer possible is letter C, 5 millimeters. That makes sense, guys? Let's write that one out. Quickly just give myself a little, do I need a transducer? Yeah, I do. I don't know if I want green. Do I want a green transducer? Sure, I do. Okay. This is a 9 millimeter. Got you 9? All right, got a 9 millimeter there. Focal point will be right there. Okay, well, let's see right there. Focal point. We have a distance to right there. You just used the wrong. And this is 8 centimeters. So the width right here is 4.5 because the original width was 9. 2 near zone lengths. The width is going to be back to the original 9. I didn't draw that to scale, but I have a hard time with that. Okay. The last question was, what is it at 5? No, at 4. What's the best estimate at 4 centimeters? So like right about here. Has to be less than this and greater than that. So they said 5. Okay, fine. What's the best estimate for the resolution at 7 centimeters? So about 5. I think it'd actually be 4.5. It'd probably be a slightly higher number than that, but it doesn't matter. We're just guesstimating. What is the best estimate for the resolution at 7 centimeters? Okay, has to be now between 9 and 4.5, but a lot closer to 4.5, right? So if we use 5, we use 5 again. Best estimate for the resolution is 7 centimeters, 1, 9, 5, and 14. We use 5 again. You know what? This is actually a great opportunity to talk to you guys about the fact that a lot of books will give you ranges, and then a lot of questions will give you specific numbers. And that gets frustrating for students. They're like, well, wait a minute. Well, the book says there's a range, and then the question in the test was a specific number, and the book doesn't say that. Yeah, but that number was probably in that range. I know question on the last test had one of those, which I'm sure I'm going to get blowback on, but we'll see. All right, number 5, what's the best estimate for a resolution at 21 centimeters? 16, 20. Ooh, so this is 16 centimeters. 21 is out here. 16 centimeters, our resolution is the same as here. So the resolution is 9. Let's just say lateral resolution is 9. So we need something that is more than 9. And our answers are 1, 9, 5, and 14's got to be, our best answer is 14. Number 6, the ability to distinguish. Let's see, the ability to distinguish when the number of cycles of pulse increases. High, low, name the force, synonyms, and 3 synonyms. I'm just going to skip to 15 and done. This is an axial resolution, right? The rest of them I feel like you could go through. The length of a pulse is 8 millimeters. So let's see, here's our pulse coming down, and that is 8 millimeters. It's hard to tell the difference between my pulse and my bracket now. What is the minimum distance between 2 reflectors positioned one in front of the other, one in front of the other? In this case, when they say one, they didn't say side by side, that's lateral, so we are talking about axial resolution. That still produces 2 images in our echo. Axial resolution is equal to the spatial pulse length, in this case 8, divided by 2 equals 4. 4 millimeters is the best we could do. Anything less than 4, we cannot tell that it's 2 different structures. Anything greater than 4, we should be able to see with our eyes that it is 2 structures, 2 separate structures. Okay, let's finish this up, baby. I really hope these are helpful, guys. I'm going to end it now.